So we're in section 3.5. So the parallel postulate is one of the most, I want to say important, maybe not important, one of the more interesting postulates that we use in geometry. It's caused a lot of controversy because a lot of people thought for a long time that the parallel postulate shouldn't be a postulate. You should be able to prove it. A lot of people have tried to prove it from various other things and haven't been able to. And I'll talk a little more about it in just a little bit. But before we write the parallel postulate, let's remember postulate. What is a postulate? What do we mean when we say postulate? Carolyn? We accept it as true without proof. So the parallel postulate says it says given a line and a point not on the line, and we're in a plane here, so we're not in space. Given a line and a point not on the line, there is exactly one line through the point that is parallel to the given line. So if we draw a picture here, it's not a complicated idea. So we have a line, and we have a point. There's our point, and here's our line. What the parallel postulate says is there is exactly one line through this point that's parallel to this line. So we can draw only one line through this point that's parallel to that line. So if I say it, we can't really say it any differently than we set it up here, so I'm not going to write it again. That's what the parallel postulate says. Through this point, we can make only one line that's parallel to this line. Any other line that we'd make through this point would either be the same line as the parallel line or would not be parallel to this line. So kind of a simple idea, but it leads to some really interesting stuff. This is not actually the parallel postulate that Euclid used. Euclid used a little different statement of the parallel postulate. This is equivalent to the one that Euclid used. This is the one that you kind of see most often in school. Again, a lot of people thought, well, we should be able to prove the parallel postulate. It seems like something that should be able to be proven. A lot of people have tried, and it hasn't been able to be proven. The other thing that happens with the parallel postulate is if you assume that it's not true, if you assume that there are no lines through this point that are parallel to this line, then you get a different kind of geometry. Instead of Euclidean geometry, you get a different kind of geometry. If you assume that there are more than one line through this point that are parallel to this line, you can get another different kind of geometry. So changing your assumptions about the parallel postulate leads to a different kind of geometry. All right, so there's our parallel postulate. Now what we want to do, yes?
How can it be that there's so many possibilities?
Well, if we accept this one as a postulate, then we get the geometry that we know. If we don't accept it as a postulate, if we accept something else as a postulate, that leads to a different kind of geometry. It doesn't necessarily match up to our everyday geometry, but it's just a different kind. All right, So now we want to talk about the triangle sum theorem, and we'll show how the parallel postulate and the triangle sum are connected. So the triangle sum theorem. We all know the triangle sum theorem. Triangle sum theorem says the measure of all angles in a triangle add to what? 180 degrees. That's our triangle sum theorem. It doesn't seem like this should have to do with the parallel postulate, but it does. It comes from the parallel postulate. So, one, I'm going to show a little demonstration as to how it comes from the parallel postulate, and then we'll do a proof. I think it's kind of nice that as sophomores in high school geometry, we now have all the mathematical tools that we need to prove something that we've accepted for basically our entire lives. So let me start this demo up here. All right, so what I have here is a triangle. Oops, do I have two pictures there? And I've constructed this red line parallel to the base of this triangle. So no matter what I do to the triangle, that stays parallel to the base of the triangle. So what we're going to do, let me move this down. What I want to do is we're going to show that, do a demonstration that shows how all of these angles add up to 180 degrees. Let me do this real quick. So what we're going to do is we're going to rotate the triangle a couple of different ways, and that will help us visualize this. Okay. So let me get this. So I'm going to take this and I'm going to select this point. I'm going to transform. I'm going to mark this point, and we're going to rotate the entire triangle around that point. So I'm going to rotate, and we're going to rotate 45 degrees. All right. So we're going to rotate, so we've rotated the triangle 45 degrees. So this angle in the triangle has rotated up to here. All right, let's rotate it another 45 degrees. So now the triangle, this angle, has rotated up to here. Anybody have a conjecture about what's going to happen to that angle? Anybody have an idea? Let's rotate it again. All right, so now we've rotated the angle up to here. What do we think is going to happen? It's going to do what? It's going to rise. Well, it's already gone above the line. What do we think is going to happen if it rotates 45 degrees one more time? What do you think? So the left side, so it'll be even with the line. What do you think? We'll make a parallelogram. Okay? All right, let's do it. So let's rotate it 45 degrees one more time. It fits right into that space. So let's color it. Let's color that one red. All right, so there's the triangle rotated right around, and this angle that was down here fits right into that space. All right, now we're going to rotate the triangle the other direction. So I'm going to take the triangle and rotate it around this point. Not that one, that one. And let's see, form, rotate, and I want to rotate it negative 45 degrees. Okay, so we're going to rotate that one around. What do we think is going to happen here? We're rotating this angle, rotate it up to here. Let's rotate it one more time. All right, what's going to happen now? Going to do the same thing. That's what it seems like, right? And there it is. So let's color that one blue. I'm rotating it right around this point. Right around that point. So if I took this blue triangle and did this, like that. All right. So this angle has rotated up to here. This angle rotated up to here. What do these three angles add up to? 180 degrees. Well, here's one angle of the triangle. Here's the other angle of the triangle. And here's the third angle of the triangle. So all three of those angles in the triangle add up to 180 degrees. So that's kind of a physical demonstration of why the triangle sum theorem works. Now let's do the proof. We have all the tools we need to do the proof also. This is kind of the idea. We good there? All right, this kind of makes a nice picture too. All right. All right, so here is our proof. So we're going to start with a triangle. Yes, so you should definitely write the proof of the triangle sum theorem down. And you guys, it's easy. It's not a difficult proof, so it's a nice short proof.
Does that work with any triangle?
With any triangle, yes. All right, so we're given triangle ABC. We want to prove that measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 equals 180 degrees. So the first thing we're going to do is I'm going to construct a line right here. Let me do it a little better here. It's not that. I wanted to do that. There we go. So I'm going to construct this line, and I'm going to say L, line L, is parallel to segment AB. What tells me I can make a line through point C that's parallel to AB? That we just talked about? The parallel postulate. The parallel postulate tells me that I can construct a line through point C that's parallel to this segment. So the reason there is the parallel postulate. Now I'm going to extend these lines out a little bit. And I'm going to call this angle 4 and this angle 5. This line, this red line, is parallel to the base of the triangle. What kind of angles are angles 2 and 4? Alternate interior angles. This is my parallel line. This is my parallel line. This is my transversal. So what do we know about measure of angle 4 and measure of angle 2? They're alternate interior angles, so their measures are congruent, are the same. Measure of angle 4 equals measure of angle 2. And we were going to say alternate interior angles. What about angle 5 and 3? Same thing. Measure of angle 5 equals the measure of angle 3. So both of those are, the reason for those is the alternate interior angles are congruent. All right. What do measures, what do angle 4, 1, and 5 add up to? 180. Measure of angle 4 plus the measure of angle 1 plus the measure of angle 5 equals 180. And why do those equal 180? Well, we have 3 angles, so we can't say they're supplementary, but what do they make? Straight angle. So we could say straight line or straight angle. But measure of angle 5 equals a measure of angle 3, right? And measure of angle 4 equals a measure of angle 2. So I can write measure of angle 2 plus a measure of angle 1 plus a measure of angle 3 equals 180 degrees. What do we call it when we take something and in an equation and put it in something else's place? Substitution. Very nice. Is that what we were trying to prove? Measure of angle 1 plus a measure of angle 2 plus a measure of angle 3 equals 180? 1, 2, 3 equals 180? All we needed was a parallel line and then alternate interior angles. And we proved that the sum of the measures of the angles in any triangle equals 180 degrees. So in October of our sophomore year in high school, we are able to prove something that we've accepted for pretty much our entire lives. And now we know why it works. Because of parallel postulates. It's November? Okay, I was hoping that it was still November. All right. Questions on the proof there? I think this is a really cool thing. That the angles in a triangle adding to 180 has to do with parallel lines. That's pretty cool. All right. One other idea that we need to talk about today. All right, folks, let's stop talking, please. Exterior angle theorem. So I'm going to say what the theorem is, and then we'll talk about what these different kinds of angles that we're talking about are. The measure of an exterior angle of a triangle is the sum of the measures of the remote interior angles. So let's draw a picture so we can see what we're talking about here. So here's my triangle. And we extend one of the sides here. Angle 4 is an exterior angle. So this is an angle outside the triangle. So we extend one of the sides and we get an exterior angle. Angle 1 and angle 2 are its remote interior angles. Remote just means far away. So the angle 4 is the exterior angle. Angle 1 and 2 are the remote interior angles. And what this theorem tells us is the measure of angle 4 equals the measure of angle 1 plus the measure of angle 2. And let's talk about why that would be. It's a really easy idea. What do angle 3 and angle 4, what do they have to add up to? They're linear pairs, so they add up to 180. What did we just decide all three angles in a triangle add up to? 180. So whatever these two are together, plus angle 3, has to equal 180. Well, this plus this is 180. So whatever these two are together has to be the same as what angle 4 is. That's the whole idea of the exterior angle theorem. All three of these add to 180. These two add up to 180. So this one has to be the same as what these are together. So that's what it tells us. All right. I just want to go through a few examples using triangle sum and using the exterior angle theorem, and that's all we have for today. So here's my first picture. All right, so for this one we want to find x, y, and z. All right, so looking at this picture, looking at this diagram, what's the easiest one to find? Yeah, angle x. So we're looking at this triangle that I'm highlighting in red. So we can split it into pieces. So we're looking at this red triangle. What do all three of the angles have to add to? 180. So to find angle x, add these two together and subtract them from 180. Or we could say x plus 32 plus 46 equals 180. So x plus 78 equals 180. Subtract 78. Pretty much just what I said here. So x equals 102 degrees. All right, what's easy to figure out next? Y. What do these two add to together? 180. All right, so 180. Y equals 180 minus 102, which is 78. The exterior angle is equal to the sum of the remote interior angle. So we could have done it that way also. So we could have said y equals 32 plus 46. Essentially what we did. All right, so now we know that y equals 78. And then how do we figure out z now? Right? So we add the two together, subtract from 180. Okay? So z, so we do 36 plus 78 equals, what does that give us? 114? And then 180 minus 114 is 66. So z equals 66. And we're finished. And there are other ways we could have done that as well. But this is nice, straightforward, easy way. All right, questions on that example? Well, z isn't an exterior angle. So Y is an exterior angle because it's outside the red triangle, but Z is inside the triangle. All right, let's look at a problem where we can use the exterior angle theorem. This is angle 1. Find measure of angle 1. All right, so again, several different ways we could do this. How could we do this by using the exterior angle theorem? Was angle 1 an exterior angle? Yeah. What are the remote interior angles? 46 and 41. Those are our remote interior angles. So we can say the measure of angle 1 equals 46 plus 41. And we add those two together and we get 87 degrees. How else could we have done this? We could figure out, well, let's call this angle X. What do all three of these angles have to add up to? 180. So we add these two together, subtract from 180, and then what do these two have to add to? 180. So we would then subtract whatever we get there from 180, and we get to 87. So you can always do it that way as well.
Wait, I have a question about your first example. If we both triangles in a big triangle, wouldn't it, like, if you combine the two, the big
Okay, that's a very good observation. So what Iris says is, couldn't we look at this triangle that I've highlighted in blue? All right. What is this whole big angle? 68. We add those two together, so that's 68 degrees. And what do all the angles inside the big triangle have to add to? 180. So that would give us a way to find angle Z. And if we added 36 and 46 and subtract from 180, we get 66. So very, very good observation. And that will come in handy for the activity that we're going to do. All right, here's another example. Yeah, that's all it asks us to do. Find measure of angle 1. I was just talking about another way we could figure it out. All right, so this one is 119 degrees. This is 2, and this is 53 degrees. And this says find measure of angle 2. So how do you guys want to do this one? Yes.
You have to subtract 180, add that,
Okay. So let's call this angle X. So X equals 180 minus 119, which equals what? 71? 61? 61 degrees. So X equals 61 degrees. And then what do we do next, Porter? Add those two. 53 plus 61 equals 114. Yeah? And then measure of angle 2 equals, how do we find measure of angle 2 now? You mean 114 from 180? And we get 66 degrees. Okay? That's perfectly fine way to do it. Is there another way we could have done it? What kind of angle is 119 degrees? It's obtuse. It's an exterior angle. What are the remote interior angles? 2 remote. We want it far away. So 2 and 53. So we could have said 119 degrees equals the measure of angle 2 plus 53 degrees. So the measure of angle 2 is 119 minus 53 degrees. And we would have gotten the same answer. Either way is fine. The exterior angle just sometimes takes a little less work. All right, let's look at one last example, and then we will be done. All right. We want to find x. How do we want to do this one? Let's use the remote exterior angle, the remote interior angle, sorry. So which is our exterior angle?
110.
110, there's our exterior angle. Where are the remote interior angles? 60 and x. Remote means far away. So we can say 110 equals x plus 60. So subtract 60 degrees, and x equals 110 minus 60, 50. Quick and easy. We could have found this angle and then say all three of these have to add to 180. That always works. It's just a little shorter. All right, questions there? Okay, homework. Yes.
Can I go fill this up?
Yeah.
Thank you.
Can I get the back of the